So we are going to have a look at how we calculate acceleration down an inclined plane. Basically, this is just a kinematics problem that first needs its forces resolved into various vectors. So the question that we're going to solve simply says a hefty man has a mass of 136 kilograms and he decides to get onto a 4-kilogram sled. He gets on the sled at the top of a 50-meter long hill that has a 30-degree incline from the horizontal. If the coefficient of friction, and again we'll assume that's sliding friction, is 0.150, then what is the acceleration parallel to the plane once the sled is released? So, as with basically every problem that we do, we need to start with a vector diagram, or a free body diagram. So first, the easiest one to probably remember is just the weight of the guy, and that goes straight down. There's a force holding the guy to the slope or the inclined plane, and we call that perpendicular because it is perpendicular to the plane. The slope will have an angle, which we have learned is 30 degrees. And that angle will be the same in here. Now, there is obviously a force pushing him down the slope, which we call force parallel. Now, force parallel, just this force here pushing him down the plane, in order for us to actually solve it, what we're going to do is we're going to make sure we solve it using a right angle triangle. So imagine we just picked up this vector and dropped it down in here. The fifth vector that we will worry about is simply the force due to friction, which we're going to call FF. So to start any problem, to determine our net acceleration, we are just going to really worry about the forces along the inclined plane. So what I usually do is I start just by writing out all the forces I need to solve. So force perpendicular, force parallel, force of friction. Now, we can't ignore the contribution of Newton's third law. Newton's third law says that for every action there's an equal and opposite reaction. So if the sledder is pushing against the inclined plane this way, the inclined plane is going to have to push perpendicularly back. So we get this normal force pressing back. And this vector will be identical in magnitude, just opposite in direction. So we're just going to write this in as the normal force. Now the normal force is simply the negative of the perpendicular force, which is probably going to help us later along. Let's make sure we can see that. Now what we need to do is we need to go along and actually solve for these. So weight is simply the mass of the object, in this case the sled plus the man, times acceleration due to gravity. So that's 136 kilograms plus 4 kilograms, that's 140 kilograms, times acceleration due to gravity, 9.81 meters per second squared. So 140 times 9.81 means the sledder and sled together have a weight of 1,373.4 newtons. Make sure we're all on the screen here. Now for the rest, the part of this that that really is different from just linear dynamics is we have to solve this triangle. So I'm just going to sort of simplify it and just write out the three forces. So I have weight, parallel force and perpendicular force in this nice right angle triangle, and I have a 30-degree angle. Now, when we do this normally, when we have a right angle triangle, normally we refer to the longest side as the hypotenuse. This is opposite the angle, and this is adjacent. So, I need to solve for force perpendicular, which is the adjacent side. So we can use SOHCAHTOA, or we can use our trig functions to try and help us here. So, for example, cosine of the angle is equal to the adjacent side. Cosine of the angle is equal to the adjacent side divided by the hypotenuse. The sine of the angle is equal to the opposite side divided by the hypotenuse. And of course, sometimes useful is tangent. So if I want to solve for this and I have weight, I'm going to use ones that have the hypotenuse or weight right into it. So either cosine or sine. I'm looking for the adjacent side, so I'm going to use cosine. So this is what I'm searching for. I have the hypotenuse, which is equal to the weight. So the cosine of the angle times the weight is going to give me the adjacent side, in this case, the force perpendicular. So we write cosine of the angle times mg, or just times weight. The parallel side, which again, remember, we've translated just down to fill in this triangle. It still is acting on the slider, but we're just going to use it to fill in our triangle. That is the opposite side. So in that case, we're trying to solve for opposite. We still have the hypotenuse, which is weight, which is the weight. So we're just going to use the sine of the angle times the hypotenuse to give us the parallel force. So sine theta times mg. The force of friction in any scenario is defined as the coefficient of friction times the normal force. But I already know what my normal force is. It's going to be equal to the negative of the perpendicular, so negative cos theta mg. For the force of friction then, I have mu cos theta mg. I'm not going to worry about that negative sign, but I am just going to multiply it by the magnitude of the perpendicular force and multiply it by the coefficient of friction. So where that leaves us is we have all of our vectors solved for, and we can use them as we see fit. We know what we're going to fill in. The perpendicular force, let's switch to black, is going to be equal to cos of 30 degrees times 1373.4. So times, making sure our calculator is in degrees, equals 1189.4. And that's, of course, newtons. Now these are forces, so the perpendicular force direction, because vectors need direction, is going to be included just in my free body diagram or my force diagram here. So then sine of 30 degrees, which is 0.5, times his weight. It's 0.5 times 1373.4 is 686.7 newtons. And the force of friction is going to be equal to the coefficient of friction, 0.15, which we're getting right from the problem, times the normal force, which is 1189.4. So 0.15 times 1189.4 is 178.41 newtons. And the normal force is simply going to be equal to negative 1189.4 newtons. And again, that negative sign is fairly useless to talk about because, again, it's all relative to what direction we're talking about. So I have all of my forces solved for. I have my weight, I have my perpendicular force, I have my parallel force, I have my force of friction, and I have my normal force. All solved out. Every inclined plane has a free body diagram with 5 vectors on it. I know we're counting 6, but remember that the parallel force is the same one, just moved down. The only ones, if there was no friction on the hill, you wouldn't have the force of friction. So there could be 4 if there was no friction, but generally there are 5. So the question asks us, what is the acceleration parallel to the plane once the sled's released? So we're only worried about the blue and purple arrows then. We're not worried about anything else. So we have force of friction and the parallel force. So we write F net is equal to the parallel force, the force pushing him down the plane, the blue arrow. And in the opposing direction, I'm going to assign a negative sign for the force of friction now. The force of friction. Again, if you were to make this negative, you could just add them because it is net force is by definition the sum of the forces. Is 686.7 newtons. Take away the force of friction, 178.41 newtons. Plus 686.7 equals 508.29 newtons. And that's direction is down the plane. We now apply Newton's second law. Force is equal to mass times acceleration. And in this case, we're talking about net force. So acceleration is equal to the net force divided by mass, which is equal to 508.29 newtons divided by 140 kilograms. Equals 3.63 meters per second squared. So now we know the acceleration of the sled as it starts to move down the inclined plane, and that we hope that's going to be constant acceleration. We're assuming the force of friction does not change. So now we have a different problem. It says, how fast will the sled be moving at the end of a 50-meter long hill? So we have a kinematics equation. V final is equal to the initial velocity. The final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times distance. We're assuming he started from stop. So Vf squared is equal to 2 times the acceleration we just solved for times the distance of the hill so Vf squared is 2 times 3.63 times 50 is equal to 363 meters squared per second squared. And I'm just going to take the root of both of those sides. So the final velocity is equal to 19 point, with 3 significant figures, 19.1 meters per second. And finally, we want it in kilometers per hour. So 19.1 meters per second times 3,600 seconds per hour times 1 kilometer over 1,000 meters. This is equal to 68.8 kilometers per hour. So the sled's going to be moving at the bottom of the hill. Part C asks the question now, what will the acceleration acting on the sled be once the sled moves onto the horizontal? So this is an area where people can struggle because we know that the sledder has run down the hill and he is now at the base of the hill. So we're talking about the point when he has moved onto the horizontal. His weight has not changed. It's still what we found above, 1373.4 newtons. His normal force has, though, because normal force is perpendicular to the plane. So let's call this normal force 2. And it's going to be equal now to the negative of the weight, just like we used to do in simple linear dynamics. So it's going to be equal to negative 1373.4 newtons. There is no other force acting in the forward direction. We do have the force of friction. I'm going to write force of friction 2 down, which is now acting in the backwards direction. There is no applied force or no parallel force now. So the only force that matters so the net force, in other words, is just the force of friction 2. It's the only force that matters. And the force of friction is equal to mu times the normal force. We're assuming mu did not change. .150 times 1373.4 is equal to negative 206.01 newtons of force. So, once again, we can just define F net to be negative 206.01 newtons. Again, I'm just going to keep the negative sign there. I think it's going to help me in a minute. So we can say acceleration is equal to F net divided by the mass, 206.01 newtons, 140 kilograms. Should probably denote this as acceleration 2, just to make my life a little bit easier, is negative 1.47 meters per second squared. Acceleration is also a vector, so the negative sign is going to help us indicate that it is opposing the motion. The next part of this problem is figuring out how far away this thing is going to slide. So, as we look at this problem, we know that the sledder is, let's just break my little mass that's a car. We know the sledder is moving. When he transferred onto the inclined plane, his velocity, sort of off the inclined plane, his velocity was 19.1 meters per second. I'm not going to deal with kilometers per hour. It's not really that helpful. So I want to know if he's going to have enough velocity or momentum to travel 75 meters. So I go back to the same equation I just used, and that was the final velocity squared is equal to the initial velocity squared plus 2AD. Let's get my vector signs on here. So I have my final velocity. I want to know when it's going to stop, so it's 0. I know my initial velocity is 19.1 meters per second. I have my acceleration. Is negative 1.47 meters per second squared. And I'm trying to solve for distance. So setting the left side of the equation equal to 0, And rearranging and solving for d, I get distance the object travels is equal to 0 minus the initial velocity squared divided by 2 times acceleration is equal to 0 minus 19.1 meters per second squared over 2 times negative 1.47 meters per second squared. So 19.1 squared is minus 0 is negative 364.81 meters squared per second squared. Is negative 2.94 meters per second squared. So second squared and second squared cancel. The meter cancels with the square, leaving my final unit in negative in simply meters. My negatives will cancel as well. So 364.81 divided by 2.94 is equal to 124 meters. So the answer is yes, he's going to run into the car. So now the final question that we're being asked in this problem is how fast will he be traveling essentially when he hits the car? So we're going to resort back to that same question. Final velocity squared is equal to initial velocity squared plus 2AD. Now I have the distance. I'm going to sub in 75. I have the acceleration. Of course, we have the constant. I know my initial velocity. I'm now looking for the final velocity again. So VF squared is equal to the initial velocity, 19.1 meters per second squared, plus 2 times. So we have 19.1 meters per second. We're going to square that, plus 2 times negative 1.47 times the distance is 75 meters. So you have to remember that it's VF squared. It seems to be an area where people get caught sometimes. So you have 19.1 squared is 364.81 meters squared per second squared plus 2 times 1.47 negative times 75 plus negative 220.5 meters times meters gives me meters squared and over second squared. So my units go together perfectly. Plus 364.81 is equal to 144.31 meters squared per second squared. So again, I'm going to get out I take the root of both sides. I get 12.01. So the final velocity is equal to 12.01 meters per second equals 12.0 meters per second. And converting, multiplying by 3.6 gives me 43.2 kilometers per hour. So 43.2 kilometers per hour when he hit the car.